This is One Angel Square in Manchester. It is the new home for the Cooperative Group. Designed by 3D Reed and engineered by Borough Happold, the 14-storey building was completed in 2013, and it is the first stage of a wider 20-acre master plan for the city.
The original brief from the client was to design a building that could bring everybody together under one roof. The cooperative had previously they had 3,500 staff in 10 or 12 different buildings. In addition to that, sustainability was a key agenda item, and that meant designing a building that was resilient to change, both physically and environmentally. We looked at how the building could be chopped and changed and manoeuvred over its lifespan, but also how it could respond to perhaps global warming and higher temperatures and more rainfall. But first and foremost, that it was an excellent and inspiring workplace for the staff to work.
The BRE's Environmental Assessment Method, or BREEAM, remains the de facto standard when it comes to gauging a building's sustainability credentials. Until recently, under BREEAM's weighted credit system, an overall score of 70% or above equated to an excellent grade, the best possible rating. But in 2008, a new level was introduced. To earn an outstanding rating, a score of 85% or more is required. To date, there are only a handful of buildings that have been graded outstanding, and with a score of 95.16%, One Angel Square in Manchester is one of the special few. This programme looks at how that was achieved. Let's start then with the focal point of the building, the atrium.
A key part of the design of this building is the central atrium, which we're standing in now. It's a 14-storey space around which wraps the floor plates.
The atrium, from an engineering point of view, offered a number of opportunities which we've maximised in the design that you see. The first one is we use it as a large duct, for want of a better phrase, to allow the air to be exhausted. So the stale air comes into the office floor plates through the floor and then makes its way out into the atrium and is exhausted at high level through the louvers that you see up at the top there. This is extremely low energy. It relies on very little fan energy, so minimising the amount of energy that the ventilation system uses. So that was the first big benefit of the atrium. The second one was the amount of daylight that it offers into a space like this. And without an atrium like this, some of the office floor plates would certainly suffer in terms of the amount of daylight that they would get towards the centre of the building.
A recent report by Davis Langdon concluded that for commercial builds, concrete can be up to 5.1% cheaper than steel. But while cost is always a key factor, at Angel Square, the team's decision to opt for concrete was governed by something else: concrete's ability to act as a thermal sponge.
We've got 330,000 square foot of exposed concrete. The concrete acts as a thermal sponge, so it captures and absorbs heat from people and computers and some solar gain. So it absorbs that heat and delays the point where we need to flick a switch and use energy to cool the building. In addition to that, we've actually painted the concrete white, predominantly because a painted white soffit allows a better degree of daylight reflection, so we can actually operate the lights at a lower lux level. So rather than 500 lux, we can operate them at 300 or 350, which is a massive reduction in the energy consumption.
The shake-up of BREEAM in 2008 put the focus firmly back on energy supply, making it the most heavily weighted category. Today, to achieve BREEAM Outstanding, an ultra-efficient and sustainable energy solution is a must.
So it became fairly obvious fairly quickly, once we'd established that as a target, that we were going to have a low carbon source of power. Now clearly on a building this scale, things like PVs or wind just isn't feasible at the sort of scale we would need it, which drew us to CHP. But CHP traditionally they run off gas, which is a relatively carbon intense source of fuel. So we needed to find an alternative source of fuel that wasn't as carbon intense, and it made sense because the co-op grow their own rapeseed, or grow their own rape, to use the seed from that, simply cold compress it and use the oil from that as a low carbon source of power to fuel the CHP engines. And all a CHP engine is just that. It's a large diesel engine that's been modified to run off biofuel, and it's strapped to an alternator, and the alternator generates energy. Obviously there's heat kicked off from that process, so any heat, rather than just being dumped out as you would in a power station, is used within the building, so is used to heat the domestic hot water, is used to heat the building.
With some 3,500 people working in the building, the use of computers can be a huge strain on that power supply. According to the Carbon Trust, office equipment represents 15% of total energy consumption in offices, a figure it says could double by 2020.
So the strategy that you see in place within the building is what we term thin client. So they have what you would call, for want of a better phrase, dumb terminals on their desks. So all the processing, or the vast majority of the processing, is contained within central server areas where that is cooled and the heat energy from there is dealt with separately. This has a couple of benefits. Firstly, it reduces the amount of power that the equipment draws in the first place, so that's a tick in the box in terms of consumption. But it also minimises the amount of, or reduces the amount of cooling that you need within the floor.
Talking of cooling, sitting proudly at the front of the building are what look like 3 large metal sculptures. These are in fact vast air vents. As Mark explains, they are portals to 90-metre long ducts known as earth tubes.
So the tubes that you see out the front of the building are the earth tubes. So there are 3 separate tubes, and what they are essentially are large concrete culverts, around about 3 metres by 3 metres in size, and the 3 of them run underneath the building into a plant room in the basement, and then they provide fresh air up to all the floor plates within the building. And the reason why they're effective in what they do is because the temperature of the ground is a relatively stable 12 degrees, roughly, give or take, throughout the year. And what they do is they draw air in through the ground and work as giant heat exchangers. So they preheat the air coming into the building, or pre-cool it in summer. And what they do is they just add a little bit of temperature modulation. They don't do all of it, but they do some of it. And it does, on a building of this scale, does make quite a large difference.
Another decision that has made a difference is the specification of passive chiller beams rather than traditional fan coil units, or FCUs.
There are 2 types of chill beams. One's active, where you blow air through it to increase the amount of cooling. The other one is passive. So these are passive chill beams. And put simply, they're a copper coil wrapped around a pressed metal ceiling plate. And how they work is they absorb the heat from the occupants, from the PCs and various other heat-giving equipment on the floor space. So they absorb the heat, take it away, dispel it out the building, and then bring back chilled water. Now the reason why they're efficient compared to other more traditional ways of cooling an office like this, such as fan coil units, is because they work at a higher chilled water temperature. So they'll work at typically sort of 15, 16 degrees as opposed to 6 degrees, which means, well, there are a couple of major benefits with that. The first one being you can use free cooling, so when the temperature outside is, say, 13, 12, 11 and below, you get free cooling. The other benefit around it is when you do need mechanical cooling, you're not trying to cool down as much. So again, there's a double benefit from installing chill beams.
Another key element of the design is the building's 16,000 square metre double skin facade. A double skin facade is simply just 2 individual glass layers that can be from 20 centimetres to 2 metres apart, with air flowing freely in between. The ventilation of the cavity can be natural, fan supported or mechanical.
And we looked at a steel option, but we discounted that because of the weight of the steel and also the potential for corrosion issues in terms of the paint finishes. Ultimately we went for a unitised aluminium system, which was cantilevered off the main primary structure. If we look at the facade in section and we start from the inner face of the facade, which is actually the thermal line, that's a double glazed facade with high performance glass to reduce the solar build-up, but we're reducing the amount of solar radiation hitting that glass in the first instance by incorporating into that interstitial space within the facade a brise-soleil system. And that's horizontal brise-soleil at every floor level that deals with the high summer sun. But we also have a series of vertical brise-soleil which deal with the low afternoon sun, particularly in the summer months. So that stops the solar radiation hitting the facade in the first place. The outer skin of the facade is single glazed. It's a weather line, but it's not the thermal line. So really that's the piece of the facade that seals the building and helps to seal in that warm body of air. So that effectively acts as a big blanket which helps to keep the building warm in the winter, and in the summer we can open the vents at the top of the facade and that allows free flow of air to help keep the building cool.
Earlier we mentioned how BREEAM's weighted criteria system puts most emphasis on the building's energy supply. But it also includes allowances for how the building is managed, the materials used, and even the health and well-being of its occupiers. Rainwater harvesting comes under the water category and can earn up to 3 credits as part of the building's overall consumption reduction strategy.
We employed a system of rainwater harvesting to capture as much of the rainwater as we could. And that works whereby we collect the water from the roof as it cascades down from the various terraces. There's a large tank just outside the front door underneath the public realm area, which is about 80,000 litres of capacity, and that is then reused for flushing toilets and the like in the building. And I think we can reduce the amount of water consumption by something like 4 or 5 Olympic swimming pools per annum.
Let's go back now to a core focus of this programme, energy supply and efficiency. As well as helping the environment, cutting energy use of course saves money. But just how much?
We would anticipate this building would save around 40, 50, 60,000 pounds per year compared to a good practice, typical building built to a similar standard. And at the very start of the project, when we were setting the targets, we compared this to a lot of the buildings within the existing cooperative group building stock, and we estimated that it would probably save around about 300 to 400,000 pounds a year compared to some of their existing building stock. So clearly there was an investment in some of the technology, but that investment should pay off.
And one of the targets we were looking to achieve was a 30% reduction in energy costs. We won't know whether we've managed to do that precisely until the systems are fully tweaked and commissioned. And we're just going through that process now at the moment to sort of log and map how the energy is being used in the building.
And this is typical for a building like this. You know, you would expect 2 or 3 years for the building to really settle down and start behaving as it should. And in fact, you know, the biggest influence on that is the people that work within the building. And this was a big change for the co-op and the way the staff worked. So those guys understanding how the building works and understanding how they can use the building to the best has taken a little bit of time.
In the UK, buildings occupied by a public authority, where the total useful floor area exceeds 500 metres squared and which are frequently visited by the public, have to display a Display Energy Certificate, or a DEC. So at One Angel Square there is no legal requirement for the co-op to do so. But as Mark explains, when those figures do finally come in, the co-op has committed to transparency.
The idea is in a prominent place within the reception, somewhere you can come up and review exactly what the meters are saying, what the gas meters are saying, what the electricity meters are saying, and how much energy the building's consuming. So that'll be continually monitored and updated on a yearly basis. But we're also really keen to share lessons learned and to share the learning experience in terms of optimising the building. So we'll be using publications such as the CIBSE Journal, so that's the Chartered Institute of Building Service Engineers. We'll probably enter the CIBSE competition either this year or next year, just to review and share with the rest of the industry the findings that we found, because I think that's really key as an engineer, and I really want to push that and let the industry learn what we've learned from the process and what the cooperative have learned from the process.
The client had a great saying at the start of this project, which was pragmatic innovation, and we all wondered what that really meant. How can you be innovative and pragmatic at the same time? But actually what we've done here is we've brought tried and tested technologies together, I think for the first time in the UK. The earth tubes, the double skin facades, the CHP powered by biofuel in the basement. So none of that is new technology that hasn't been tested, but it's perhaps bringing those things together for the first time in a commercial environment and making it commercially viable as well in the marketplace, which makes this project unique.